All right, so we are starting chapter 7 here before we go for spring break. So 7.1 is graphing systems of equations. So we're going to be solving systems of linear equations by using the graphing method. And we just came off of this whole unit of graphing and looking at slope and how to write equations and all those things. That's going to be helpful for us. And we're going to recognize the 3 possible types of solutions for a system of 2 linear equations. Okay, so first of all, when it says a system of linear equations, it just means 2 or more linear equations or equations. So we might have, or I can look at this one. This is a system right here. This is a system of equations. It's 2 equations or 2 lines that have to go together. They are related. Okay? A solution to the system is where those 2 things, those 2 lines intersect. Okay? That's what the next thing says. An ordered pair that makes all of the equations true is a solution. Okay? It is their point of intersection. Okay, so we're going to have some different options about where lines intersect, but you have to find the ordered pair where the 2 lines intersect, and that will be their system, or that will be their solution. I'm sorry, the solution to the system or their solution. So in example 1, first of all, we want to determine whether each ordered pair is a solution to the system. That's all we're going to do is this ordered pair a solution to this system? Okay, so we are going to plug that x and that y value into the equation, into each of those. And in order for it to be a solution, what has to happen? Do you know? It has to be true. It's like your favorite guess and check, right? Like favorite problem solving, guess and check. This is our guess. We've got our x comma y as always, and we're going to plug them into each equation. So for our first one, we have x minus y equals 9. My x is 11 minus my y is 2. That equals 9. 11 minus 2 is 9. Sweet. So does this mean it's a solution to the system? No, you didn't check the system. You checked one equation. A system is made up of 2 or more. So, yes, it works for this one. Now I got to check the second one. So 2x plus y equals 9. So I'm going to have 2. My x is 2. So 2 times 2 plus y. Oh, hurry, my bad. All right, so 2 times my x, which is 11. There we go. Plus y is 2. And that equals 9. 2 times 11 is 22 plus 2 should equal 9. 22 plus 2 is 24. Does 24 equal 9? No, but I had to check both equations. And so determine whether each ordered pair is a solution to the system. What can we say? Not a solution. Okay, so we would say not a solution. You could write to the system if that helps remind you. But yeah, this one is not a solution to the system. Okay, because both of them, it has to create 2 true statements. So for B, we're using the same system. This is still my system. So in my x minus y equals 9, I'm going to put 6 minus -3. That's another trip up. Like you have to put 6 minus, and -3 is your y. Okay, when we have minus and negative, what is that? It's just plus a positive. So 6 plus 3 is 9, which equals 9. So hey, that one checks out. But what do I have to do now? We have to do the second one, the second equation in the system. So 2x plus y equals 9. All right, so 2 times x, which is 6, plus y, which is negative 3, equals 9. So 2 times 6 is 12, plus negative is the same thing as minus 3. 12 minus 3 is 9. So this one checks out. This one is a solution. No, you need to put that it's a solution. That'd be fine. So yes, this is a solution to the system. Okay, very rarely is that how you're gonna be, are you gonna be asked to do that, right? Like we're just introductory here, starting off. So determine if it's a solution. So now we know what a solution to a system would look like. Now we're gonna start solving the system by graphing. All right, like it says there, okay? Solving a system by graphing. We've got some steps. We're gonna graph both equations on the same coordinate plane. You are given a coordinate plane, and here is your system, your equations. You're going to identify the point of intersection. This is the solution. And then you're going to check the solution by substituting it into each equation. Okay, want to check. So we will do that once or twice. We won't do it for all of them. Okay. Now, the nice thing on example 2a, these are already in slope-intercept form. So they're very simple to graph. We look at our b, right, -2. So I go to -2 and I put my point. It's my y-intercept. My slope here is -1. So I go down 1 and over 1. Or I'm going to go down 3 and over 3 to spread out my points. And then I'll go up 3, 1, 2, 3, and over 1, 2, 3. Okay? I chose to go down 3 and over 3 because that's the same thing as down 1 and over 1. But instead of going 1, 1, 1, 1, 1, 1, I wanted to spread my points out a little bit. So I said, oh, 3 over 3 is the same thing. It's equivalent to 1, or you could pick 5 over 5, or however. Okay. Let me graph my other one a different color. All right, so this one, again in slope-intercept form. My b is -4. Why am I not changing colors? Okay, so my b is -4. So I'm going to go down to -4, put my y-intercept. My slope here is a +1. So again, I'm going to go up like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Hopefully on yours. Okay, don't forget your arrows. So I graphed both equations. That's step 1. My point of intersection. What is my point of intersection right there? 1, -3. And that point of intersection is my what? Solution. That's my solution. And so now I need to check it. Okay, so y is -3 equals -1 minus 2. -1 minus 2 is -3, so that one checks out. For my other one, y equals, so I'm going to have -3 equals x, which is 1 minus 4. Okay, so -3 equals 1 minus 4 is -3. It checks out. That's my solution. Got it. Ready to go. So my solution, you're going to write down there on that line, is 1, -3. That is your solution. All right, the second one is going to require more work. It's not in slope-intercept form. It's not easy to graph. So we have to do the work from last chapter to put it in slope-intercept form. So we've got x minus y equals -5. Subtract x. Then we have -y equals -x minus 5. Divide by -1. And that's going to give us y equals x plus 5 as one of our equations. And for the other one, we have 3x plus y equals -7. Subtract 3x. Y equals -3x minus 7. That's our other equation. Okay, so got to get them into that slope-intercept form so then we can graph them. You don't have what? Oh, we go to, do you mean to graph it? Yeah. Oh, okay, fair enough, yes. So to graph it, right, our y-intercept here is 5. So we go up our +5, 1, 2, 3, 4, 5. And our slope is, what's the coefficient, the number in front of the x? 1. It's not there, but it is. We're just lazy mathematicians that don't write it. So it's 1. So we're going to go up 1 and over 1. Right? Or you can go down 1 and left 1. Okay? And graph your line. What's your question? We are doing equations, not inequalities. Only when we do inequalities. But we will do inequalities. But then there's shading involved. There's dashed and shading. And so it will be where the shading overlaps when we get to when we get to that later. All right, so for our green one here, y equals -3x minus 7. Our b is -7. So we're going to go 1, 2, 3, 4, 5, 6, -7. And my slope is -3. Okay, what is that as a fraction? -3/1. So that's important to remember. So you would go down 3 and right 1. Or you could go up 3 and left 1. And so where is your point of intersection this time? -3, 2. All right. All right. So you could plug that in and check it again. So 2 is going to equal -3 plus 5. Does that work? -3 plus 5 is? No. Right, -3 plus 5 is 2. So that one works. We're going to plug it into this one. So 2 should equal -3 times -3 minus 7. Okay, so 2 should equal, what's -3 times -3? No.
Oh, I mean 9.
9, because a negative times a negative is a positive. So we've got 9 minus 7. What's 9 minus 7?
2.
So 2 equals 2. That one checks out. So it is indeed your solution, -3, 2. All right. Now, parallel lines. Parallel lines have no solution. None at all. Why is this the case? How can parallel?
They have the same slope or something?
They do have the same slope, but how come they don't have a solution in a system? What's the answer to a solution? Or what is the solution to a system? It was the what? Their The point of intersection. Show me some parallel lines with your arms. What do parallel lines look like? Where do they intersect? Nowhere. So how come parallel lines have no solution? Because they don't intersect. Ding, 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 ding. Okay. So parallel lines will never, ever, ever have a solution. Okay? Now, we also have coinciding lines. They are the same line. Okay, so it's when you have one line and another line is right on top of it. They're the exact same line. Those are coinciding, okay, with each other. And here, the solution is the set of all the points on the line. Okay, because every single point matches up because they're the same line. The equation might be written differently, but they're the same line. Okay, so we're probably going to see examples of these two things in example 3. Right? I know, it's a shocker, isn't it? Okay, so we're not in slope-intercept form. So we're going to take that x plus y equals 3, subtract x, and get y equals negative x plus 3 to graph. And we're going to take this to my board. We're going to take this 2y equals negative 2x plus 6, divide by 2, and get y equals negative x plus 3 to graph. Wait a minute. What do you notice about this equation now and this equation? They're the exact same thing. They were not the same in the system. But when you put them in slope-intercept form, it's very easy to see. Like, these are, in fact, the same line. So what kind of line are these? Or lines are these? They are the exact same line. What? Coinciding. These are coinciding. You weren't the only one that said it. These are coinciding lines. Okay, but we still need to graph them. So 3 is our intercept, our y-intercept. Our slope is negative 1. And we draw our line. And we put arrows on the end.
Wait, so are you going up 3 and over 1? Or?
No, I went up 3 and I went left 1. Or I went left 3. Because, like, I went up 1, oh, left 1, up 1, left 1, up 1, left 1, and put a point. Excuse me. Would it be what? Oh, valid question. What do you guys think that you write for the solution? No solution. No. Would it make sense for us to put no solution?
No, but that's what you just said.
That's what somebody else said, and I repeated it. Okay.
All real points?
Not all real points. Good try. All good guesses.
Would we put the equation as the solution?
Ding, 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 ding.
I literally was like, no.
So you're going to put the equation in slope-intercept form. Yep. You're going to put the equation in slope-intercept form because it's the exact same equation. The only way to get every number on that line would be to include the equation. Good. Okay, so then on the next one, again, we don't have slope-intercept form, so we're going to take each of those and get them into slope-intercept form. So we subtract x, y equals negative x plus 3, x plus y equals 7, subtract x, y equals negative x plus 7. Okay, what do you notice about these two equations now? They're not the same. Good. What do you notice about them? Okay, but they don't have a positive, okay, but they have a positive 3 or a positive 7. Your previous statement, they both have a negative x. What does that mean about them? Why are they parallel? No, that's if you graph it. How do you know from what we're given here? Anne said they both have a negative x. You drew the conclusion they're parallel. How do you know they're parallel? Again, this comes back from last chapter. They're not going to both be on the same line. They're not coinciding. So no. What is the negative x? What's in the negative x?
-1.
What means -1? What is -1?
-1x.
No. She said they both have a negative x. Yes, but what's embedded in that negative x that you need to pull out of the equation?
Slope.
The -1. What is the -1?
The slope.
The slope. Okay, okay. So we know the slope of this equation is -1, and the slope of this equation is -1. What do we know about lines when they have the same slope?
They're parallel.
They're parallel. Okay, so like we're gonna graph it and prove it, but like again, last chapter, like slope-intercept form, all of those things, they're coming back. They're never disappearing. So y-intercept is 3, and our slope is -1.
Guys, we can't have Brandon thinking we're morons. Yeah.
This is true. Okay, so there's my -x plus 3, and then I have a 7. 3, 4, 5, 6, 7. So, you just proved by graphing that these are indeed parallel. So what is the solution? No solution. No solution. Because it says, right, it says down below. It also said it up here, right? Parallel lines have no solution. I tend to repeat important stuff in the notes, even in writing, not just in talking. I'm sorry for all the coughing, Brandon. All right, so that one has no solution.
Wait, I'm sorry. So it's -7 or 7.
Uh-huh.
And then you go up 1 or down. What? What?
Okay, because the slope is -1.
Yeah.
Yes, you can. That's -1 over 1, which means I can go up 1. That's positive, and then if that means my negative would be down here, so I would go left 1. Or I can go down 1 and go right
Oh, okay,
1.
never.
Okay, so I can do any of those options. Okay, then at the bottom you have a chart that talks about your possible solutions to a system when you graph it. Okay, so you can have intersecting lines, which is going to give you one solution, and it's going to look like an ordered pair. The parallel lines are going to have no solution, and so there is no answer. Coinciding lines are going to have infinite solutions, and it's going to be all the points on the line. So you might make a note here that you write the equation of the line. Okay, so your answer, you're going to write the equations of the line there, so you remember. All right, and then you can get started on the work.